Hi, everyone. Today we are going to look at generative AI model hosting, and we are going to look at how do we host at scale on SageMaker. We're going to be looking at a couple of options. So first, we're going to dig into what are the challenges, the key challenges which we face when we are trying to deploy a model for inferencing or hosting, as different people tend to call those words. And then we will get into what are the potential solutions, how SageMaker has addressed some of those challenges and solved them. And then towards the end, we look at the demo. So we look at a couple of two different models on SageMaker. And we will also cover Inferencia, the latest offering, to get a better price performance ratio. So let's look at large models. What generative AI has come of age undoubtedly since last year. I would say towards last year, it has been one of the most popular topics across the globe. And the reason I say across the globe is, just connecting personally on this aspect. I was talking to my parents in India a couple of weeks ago, and my mother was asking about how does she open a Chat GPT account, so which tells me that if that generation who was not seen, for which electricity was, I would consider a luxury, if that generation is now asking about Chat GPT and open and how do I go large models, it has come of age. So what are the challenges in hosting the large models, right? If you look at the large models, your key challenge is the complexity. And by complexity, what I mean is the model size. The model size are increasing. We have 1 trillion parameter models now coming up, so hosting them and fitting the model in a single GPU is challenging. You could have different workflows. You could be invoking a series of models before an inferencing result comes in. You could look at your batch size, and some of those expertise need to become. So that's the first dimension, right? I tend to call this as a trilateral problem. The second dimension is, of course, is your performance, because you are trying to have a low latency. You look at the chatbots. The chatbots are effectively human has, as somebody told me from psychology, like 2 seconds before they tend to zone out. So you need to have a response time less than that. And you're talking of a large language foundational model trying to respond within that time. And then you have multiple users, so your throughput is increasing as well, and you're trying to balance all that with cost. So these are three different dimensions. They're pulling in each direction, and you're trying to effectively see how best can you host, keeping all these parameters in line. Take a simple example. I'll take GPT-J. So GPT-J, we'll not get into the training. We're going to talk about the hosting, but the training is roughly about 200 gigs. If I talk about model serving and FP32 weight, and I add, if I, let's say I ignore the checkpoint, right? So I basically just have the initial weights, which is a 24 gig GPT-J 6 billion parameter. I add the batch size. I'm roughly talking close to about 25, 26, 30 gigs roughly of memory capacity, which I need for a GPT-J. And then, of course, on top of it, you have a framework specific memory allocation, your CUDA context, which need to be managed. So all of this put together can vary from between 24 to 30 gigs per model which you're trying to host. And of course, in FP16, you're going to reduce this by half. So FP16 would be roughly about 15 gigs, right? So how do we solve this challenge? How do we solve this problem? So the first problem we have effectively is, how can I fit a model in GPU? If I take A10s, A10s are about 25 gigs in size. If I look at A100s, they're about 40 gigs. P4Ds, P4DEs are about 80 gigs in size. So take that kind of a model, Bloom 176 model. The first technique we apply is try to apply compression on the model. By that what I mean is, you are able to reduce the number of layers for that specific use case. So essentially what you're doing is we are pruning the layers between the weights. So a dense layer like this may actually convert to a simpler matrix on the right hand side, which is the first technique, which will reduce the size of a model which you need to host. Knowledge distillation is one of the most common techniques. It applies to pre-hosting, I would say, considering training realm. So I'll skip that. The second technique, which is quite often applied, is quantization. By quantization, I mean is you have your weight sizes in activation, you have your weight sizes in your last layers as you're trying to go through the forward pass of the model, and most of the models are usually in FP32 bit weight. So FP32 is a 4 byte. You basically multiply that by number of parameters. That's what gives you your model sizes. You reduce this to an int 8, you're slashing your model size by 4 right off the bat. Now, of course, what this means is you are going to start to lose precision. And so there are there are other parameters available like BF16, which can also optimize, but those depend on the model. Is the model supporting BF16? Is the underlying framework going to support BF16 quantizations as well? Assuming we've done all of that, we have been able to reduce the size, or we're not able to reduce the size depending on the use case. Now the second question is, okay, I've got this model. Let's take a 55 gig model, which is a FLAN T5 double XL large model, right? A 55 gig model, I'm trying to fit it onto a 25 gigs of A10 instances. I will need a couple of these to fit in here. So the first technique, what we apply is what we call is tensor parallel. In that, what we're doing is we are sharding across the horizontal layers. So each layer will go and sit on a specific GPU. The downsize, or rather the trade-off, is you are effectively going to now have inter-GPU communication, which is going to increase. So how does that work? Let's take a look at the animation. So you effectively are sharding horizontally. The layers go in each one of these GPU devices. I get my inference data, they move across, but I have now trade-off a higher GPU communication, and so my weights are going till the time I basically get a single result towards the end. So that's the first technique. The second technique basically is what we call as model parallelism or pipeline parallelism, where you are sharding vertically. You're basically placing each layer on each one of the GPUs. Now, the challenge here is that GPU 2 can only be working when GPU 1 has finished. So now you can see I'm starting to add a little bit of sequentiality in the processing, which means I may not be able to optimize the GPUs as effectively as I can in the earlier state, because our goal is to keep all the GPUs maximized and activated. So that's just one of the few techniques we looked at, how I can take a model which was not going to fit in a single GPU, and how do I effectively make use of a multi-GPU instance, and how do I fit as part of my hosting challenges, right? So in SageMaker, we've taken a look at this problem, and we're going to focus on the deployment side of this. I'm going to skip to the slide where I am going to look at the solution in SageMaker for the challenges we just looked at. And in SageMaker, what we have is effectively what we call as a large model inference container. This is the latest offering from SageMaker, purposely designed for hosting large models in SageMaker. So the 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 first challenge we had in SageMaker was, okay, I've got, let's say, Bloom's 176, which is a 350 gigabyte in size model. How do I take a 350 gig model and load it onto the container? So we effectively now are allowing a higher EBS volume. So you can go up to 500 gigs on the EBS volume, which get attached to the endpoint, and lets you now fit the model onto the instance. So once you've got the model onto the instance, the next step is now loading the model onto the GPUs or the CPUs. And so for that, in the large model containers, we basically are giving you almost no code, low code option. And I will show you as part of the demo of how you can achieve model compression, how you can achieve model partitioning as part of our containers. So let's look at the stack. If you look at the stack, we are talking of the section on my left is, I would consider, still in pre-training, post-training realm, where what I'm doing is I'm using model compilations to reduce the size of my model. So there are libraries and frameworks available, TensorRT, DeepSpeed, Faster Transformer being the latest one. And in this in this compilation technique, you will have a no hit on accuracy and no hit on performance. By what I mean by that is, since you're compiling the model to a specific hardware, you are effectively injecting kernels for that specific hardware, which are optimizing your performance and optimizing and keeping your accuracy the same. So that's really where the model compilation tends to score. Regardless of your workload, it is something we always recommend. Always go for model compilations. Post the compilation. Now, say I've done my model compilation, right? I'll take an example. So I've got a 350 gig, a 350 gig model, which I've compiled down to, let's say I've reduced the weight by, let's say 200 gigs, right? I'm just throwing a number out here. So again, it will not fit in any one of our known GPUs. So now I have to still look at either quantization or and/or partitioning. So quantization, I'm reducing what we looked at earlier, reducing the size of the weights. In that case, you are going to see a little loss of accuracy. And so your accuracy is going to go down, your performance gains are going to be there. So that's a trade-off. Now, having said that, always the recommendation is to do your model functional testing, where you're looking at the model outputs, comparing them to your known database sets to see the output is in line with what your use case is, and make sure that happens before you proceed further. And the second technique, once you've done the quantization, let's say I've done the quantization, brought it down to 90 gigs in size. Now I'm still trying to host it on the largest A100s 40 gig GPU instances. I have to partition the models in the way we show. Either I can use tensor parallelism or I can use pipeline parallelism, or both of them. In that scenario, whichever option I choose, I will have an increase in GPU communications. That's why my performance and my latency may see a slight dip. Again, it depends model, depends use case, depends hardware. There are a lot of variable factors here, but I will not see a decrease in my accuracy as part of my model partitioning. So that's the key takeaway. Now, when you look at all of this and you say, hey, that's a lot of things I have to do. I have to worry about compilation, compression, model partitioning, and then I have to manage all this infrastructure. That's a fairly significant heavy lifting. And that's where LMI tends to score effectively in SageMaker. In SageMaker, using LMI, you are able to just take you're able to take the raw weights of the model from this point, and you are able to get it down where you can now fit it into multiple 40 gigs GPUs. Let's say I'm able to fit it in two of these GPUs with only defining certain properties, and it's a no-code option in LMI container. And then, of course, we have benchmark numbers, and this deck is available on Wisdom, so we'll be very happy to share some of those benchmark numbers as well. But what I would like to cover is let's maybe we can stop here. So this table is what I wanted to show you, that when you look at the quantization, which is one of the most popular techniques, there are a few parameters to be aware of, whether you're looking at deep speed, TensorRT, or faster transformer. And the key point to take a look at it is, do they support what we call as BF16 option or not? The reason I say that is BF16, as at a high level, basically splits your number in two parts. So there is a first part, which is the mantissa, and then is the exponent. Each is basically 1 byte each. So you are able to take, instead of 4 bytes, and you have precision, high precision, you're able to still retain significant precision and not sacrifice on that by going all the way down to int 8, right? So that's where the BF16 tends to score, and there are a lot more support from the models coming out for BF16. So be aware of that. Which quantization libraries are you going to use as you're going through BF16 quantizations? And so I'd like to leave you with this picture. This picture goes into, okay, here is where the LMI container is able to help you with the partitioning, able to help you with the quantization, and also able to load your models across multiple GPUs. So that's very good. Now, there was one problem which we kind of skipped, and now we'll get to that problem. And that problem is I've got this 350 gig model in S3. How do I get this into the container? And so getting this into the container, when I ran the benchmark numbers, took me approximately an hour just to load 350 gigs into the container. And you have to load it first into the container, and then you will, use all of these good things to load into the memory. And so in the LMI container, we looked at the problem. We effectively found a solution in form of S5 CMD. And so if you specify your weights in S3, we are able to use that library, which is massively parallel library, to load these weights. Now, in the testing which I did, loading a 350 gig model is roughly about 4 minutes or so, compared to 30 minutes, which is taking. Now, of course, if you have your weights already pre-compiled, or you have your weights quantized in S3, this time comes down to a couple of seconds. So most of the models we're looking at is a couple of seconds to load from S3. And that's a very significant process improvement which the LMI container brings. And for those who are familiar with SageMaker, you are aware that SageMaker needs you to create a model.tar.gz. So now imagine having to create a model.tar.gz just for this 350 gigs model. When I did this for the first time, it took me about 4 hours just to create the tar ball itself. So imagine if I have to now iterate over that model, the amount of time it takes to create the tar ball, get it to S3, get it to the container, and all that is pretty significant, right? So in LMI, what we looked at is we said, hey, we really don't need the tar ball. We basically just need the raw S3 location. So you can now have your weights in the raw form in S3, and just point your DGL container or the LMI container to that, and it will automatically take care of loading the weights and making it available in your inference script. And behind the scenes, it'll take care of mounting the EBS volumes correctly, mounting basically where the temp directory as part of the container, because that is where most of the weights go. So enough of theory, enough of what we have looked at. Let's look at some of the code, and what we will do is we will look at two models. So we look at an NLP offering. That'll be a FLAN T5, a double XL model. It's roughly about 55 gigs in size. And then we will look at Neuron SDK as well. We will look at Stable Diffusion on use compiled with Neuron SDK and then hosted on SageMaker. Now, I do want to point out this notebook is available. Most of the code which I'm going to show you is available on SageMaker examples repo. So you will be able to just take the file and run it. And on top of it, what we have also done is worked with the legal team and worked with our partners in the SageMaker examples repo to make the weights available in public S3. So you really don't have to go to the Hugging Face hub, download the weights, do the compilation. We made that available for you. So you can just take this notebook and pretty much run through the notebook as is, just to get a flavor of how would you do some of the work. So let's take a look at some of the important sections in this notebook, right? So before I do that, let me actually run the model. Let me run the model and show you how the model looks like. And then we can take a look at what it takes to get to this point, right? So I just basically ran a simple prediction. The World Cup has kicked off in United States. Based on that, can we conclude the World Place will take place in United States? Yes or no? So this is a FLAN T5. It is trained on the open source. So the answer which I get is yes, based on the prompt I've given. And actually, this notebook gets into a couple of prompts. If you're interested in prompt engineering, we are getting into common sense reasoning. That's the example I showed you. There is sentiment classification, article generation. But let's take a look at abstractive question answering. So there is a chat which happened between the customer and the agent for an iPhone. And the customer is having some issues with the iPhone. He's trying to reset this. And so here is basically what the chat looks like. And then I ask a question to the model saying, hey, model, based on this input, can you tell me that if the troubleshooting steps which were taken Are they fixed or not? So when I run this, let us see what the model basically will tell me. And based on that, the model is able to summarize what happened in this chat. And it said that force quit the apps as they're using a lot of battery, reset, etc. So the kind of thing it picked up. So it was able to take that context and you in the host this. Why am I showing you this? Is because it is important when we are doing all the techniques of quantizations and of sharding, we need to make sure functional output makes sense. We are not messing up or having garbled output come out of this. Second question we ask a series of this, was the resetting solve the issue or not? And then if I run this, it basically tells me no based on the inputs which I've given, right? So this is how the model is now performing. So let's look at what it takes for us to get to this point. The code which I'm going to show you is basically talking about is a low code or a no code options. By low code, I mean is you really do not need to bring your Inference script. There are default handlers which are available in LMI. So you're able to bring your Inference script and just load from there. And let's take a look at some of the parameters. So to create the magic which we just saw, all you need is what we call as serving.properties. That's pretty much it. You just basically say, okay, here is my S3, here is my serving.properties, here is my container. Now go deploy, run, and I can kind of leverage this. In serving.properties, behind the scenes, we are doing a lot more things which are going on, right? So the first thing is start from the first place. I've got my model in an S3 location. Okay, move it to the container. What do I need to do? I need to basically specify an S3 URL. I say, here is the S3 URL, point to the top level folder where all the weights are. And behind the scenes, S5CMD is used to just quickly copy them into the container. The second thing which I tell the LMI container is what is the engine which I'm using. Now, this is interesting because I can use deep speed, I can use faster transformer, I can use Hugging Face accelerate. Those are very standard libraries which are being used to shard your model across GPUs. So in here, I'm basically going to specify faster transformer as the engine which I want to use because I'm going to use faster transformer. In fact, in our testing, benchmark testing, we find faster transformer to be the fastest in terms of the inferencing for the same model using faster transformer, D speed, and accelerate. And then I have an option of specifying the entry point. Now, if I give an entry point, it will use this. In our case, because it's a low-code option, we will not specify this parameter. If you want to bring your own script, you have the option of specifying this, and the example GitHub will actually go through this. So instead of this, we are going to specify, I'm going to use faster transformer, DJL python.faster transformer, and that is actually going to go to the inbuilt handler, and it's going to pull the inbuilt handler file and then use that to serve the model. So before I show you this class, let me talk about the tensor parallel degree first, and then we'll take a look at what is the inbuilt handler doing. So tensor parallel degree is what you can use to specify the number of GPU devices over which you're going to partition the model. So I'm using a G5 12x large in here. That's a 4 GPU machine. And if I set a tensor parallel degree of 2, that means it is going to effectively shard my model across 2 different GPUs. Now, what that also means is that means the default number of workers which I will get will also be 2. Because if I'm using 2 GPUs, they're fully saturated by model 1, and I have 4 GPUs available, then I can effectively have 2 workers, so I can increase my throughput based on that. So that's the key points which you want to take away. And if you see over here, in this case, I'm specifying a tensor parallel degree of 4, so I'm going to have only 1 worker behind the scenes, and I'm sharding my model across all the 4 GPUs as part of this. And I use the faster transformer entry point. So let's take a look at the faster transformer class, right? Again, this is part of the GitHub deep Java library from our AWS service team. and you can take a look at the class. It's open source, it's Apache license. So the key points to note over here is that when you are, I mean, you don't have to actually write this class. You may not even need to look and kind of, just understand what this class does. You really don't need to do all that. I'm just showing you behind the scenes. If you want to bring your own model.py, you can leverage some of these properties over here, right? The key parameter which you're looking for is what is the quantization I'm going to use. So there is a D type available. If you do not specify anything, it is going to default to FP32. Now, you can do ahead of time quantization, which means theoretically you could have had BF16 weights in your S3, in which case it will default to whatever the weights are there. But we are using full precision as part of this. And then your key method over here is load model. In the load model, all I'm doing is taking the faster transformer and running the init, give it the tensor parallel degree, and also give the sharding parameter which I need. Now, this is an interesting line of code. It looks pretty innocuous, single line of code, but if you really look at it, in this single line of code, I have sharded the model and I've also quantized the model at the same time with this single line of code. And that is where the LMI containers really tend to, just start to show the value of SageMaker as we are trying to deploy the large models. The input into the class, or rather what the class does is it just needs you to have, you want to do your own model.py, for example, right? You basically just need to have one method, which is called handle. And in this method, and it's a functional programming paradigm, so the entry point is a single method. From this single method, you're basically just, doing a fan in, fan out for various methods, classes, whatever you want to do. Now, the reason I'm showing you this is because I wanted to take a look at this call here. When the DGL server comes up, the first thing it does is it makes a warm-up call to the model on startup, and in which case it is not going to have an inference payload. So if the service is not initialized, create, load the model, and the model gets loaded. It does all the tensor parallelism and so on and so forth, and then for the warm-up call, the inputs are going to be empty. And subsequently, when the user starts to make the request like the way I did, you will have your inputs come in. And then, of course, there's a whole sort of model parameters which go through some of this. So that's how this model.py or faster transformer.py class has been built. Once we've defined our serving.properties back to SageMaker, how we're going to run through a model, here is the location of the public S3 weights for Plantify. All we are doing effectively is then just creating the endpoint. And for the endpoint, what we're going to do is create a model.tar.gz. And if you remember, I told you we don't need to have the raw weights in the tar.gz. So the tar.gz has only serving.properties. That's it. Pretty much that's the only thing which we have. The tar.gz takes less than a second to create this and less than a second to upload this into S3. Rest of the steps are the same in what we would do for any deployment in SageMaker. Basically, just create take the image, and the image here is a faster transformer. Create my endpoint, which is I'm going to create a model object, and from the model object, give me instance type, which is D5 12x large, 4 GPU, 25 gigs in each GPU, kind of an instance, and then just do a model.deploy. And once I have my model deployed, just create a predictor class out of it. And once I'm a predictor, I can now use the predictions to run some of the inference load which I want to do. That's pretty much it, what it takes to host a large model. And there are a lot of examples in here which are going through. So the key takeaway is you have an option now of hosting a large model in SageMaker using LMI container with absolutely no need to bring your own inference file, no need to worry about how sharding and parallelizations and all those good things are going to happen. All that is taken care of behind the scenes for you by the LMI containers. And feel free to play around with this notebook. It has some good examples. Try your own, bring your own model if you want. Hugging Face, there are a lot of options available. There is one option I did want to point out as part of this. You also have the option of specifying the model directly from the Hugging Face hub if you are interested. So you don't have to have the weights in S3. That is an option. There is a model.id. And if you want to use the model.id, just point it to a Hugging Face repository, the Hugging Face model object, and it will on the fly download the model, do all these steps we spoke about earlier, and then deploy our model. Of course, it's going to take longer because you're now going to download the full model, and then you're going to, of course, be able to load it in GPU and then continue further, right? So, but that option remains. So if you want to do a quick test, point to this model, run it, see if it works well, point to another model, run it, see if it works well, and so on. Now, if you have additional libraries which you want to bring in, you can bring requirements.txt file, and it will essentially do a pip install behind the scenes when it shows the pip install, and it kind of runs through. So once the endpoint comes up, I actually wanted to show you how the endpoint may look like when the endpoint is coming up. So captured those logs, and I will zoom this because I just wanted to make sure I can kind of show you how the logs are going to look like. So once I zoom, let me see if I can zoom from here. So I'll zoom this to about 150%, right? And let me actually zoom a bit more. Let me go all the way to 200%. So now when the model starts, when the container starts up, um, it will essentially give you the number of CPUs. It will give you where the model directory is. It will also give you your batch size. Most of the NLP and any generative AI batch size is always something which is recommended. So we support the batch size, but we also have a batch delay standard parameters for any NLP model. And so it gives you those configuration values, right? What have you specified? And then from the logs, you can also see if the model got downloaded, where it is getting downloaded from, and did it download successful. Once the DGL server starts up, SageMaker does a ping. You will basically see a log, something like, okay, here is the address it is bound to, here is the port number, and your endpoint is now up and running. If you're more interested in seeing, okay, what are the parameters of DGL server, it will give you that as well, and it'll point out some of the arguments in your when it's kicked off the DGL serving. So that's about the NLP. That is about how would you host a large model, uh, any NLP large model using LMI containers. Let's switch gears. Now we are going to take a look at stable diffusion, and let's see if I can host a stable diffusion, which is text to image kind of a workload on LMI containers. So Inference 2 got launched recently. It's been announced, and as part of Inference 2, the LMI container now supports the Stable Diffusion 2.1 on Inference 2 workloads as well. So the key benefits you get from the Inference 2, one is like when I ran my benchmark numbers, I took a G5 12x large and I took Inference 2 8x large instance. Um if I do the same kind of quantization on a stable diffusion, sorry, if I take the same kind of compilations on a stable diffusion model with BF16 accuracy, I was getting 1.9 seconds as latency, but my cost of Inference 2 is almost half compared to G5 12x large. So that's the gains what we start to see with Inference 2. And Inference 2 actually comes with if you look at the design of Inference 2, it basically comes, each chip comes with two cores. And each core, where Inference 2 starts to benefit a lot is each core has different engines to perform different aspects of the inferencing. So it has a vector engine, it basically has a tensor engine and a scalar engine. These are really the key three any matrix operations which are performed in any sort of workloads, right? Be it NLP, be it your image processing workloads. So we have specialized areas in the chip which handle this, and that's where Inference 2 starts to score up. It's able to do the same workload on less capacity. Now with AWS Neuron, you do need to compile the model. So the Neuron compiler, and we will give you the notebooks where you can actually take a look at how the Neuron compiler is able to compile some of these models. It effectively compiles the model into what we call as NEF format, which is Neuron executable file format. And behind the scenes, it is what it's doing is taking our model, looking at the kernels, replacing them with the Neuron runtime kernels and the C++ libraries, which are highly optimized for throughput and low latency. And that is really that is all pretty much what we need to do for Inferentia to host a stable diffusion 2.1 version on Inferentia 2. So there is a blog post which goes into the details of what the Inferentia 2 looks like. And if you search for achieve high performance on Inferentia 2, you'll be able to find it on Google. And but we'll include the links as well for some of the containers. So now let's look at, okay, how does Inferentia 2 really look like? So for Inferentia 2, I basically have the Inferentia 2 set up on, I'm going to show you through VS Code. This is running on SageMaker endpoint, and I'm generating a 512 by 512 image using the SageMaker endpoint. So this I just gave it a prompt saying mountains landscape, and it basically generated this image. What you can see as part of this. I'll zoom this, so we'll talk a little bit more about the code itself, right? And this will be available in public SageMaker examples repo, so you should be able to get it from there. Now the concepts are almost similar to what we were seeing earlier. So the first key concept is, okay, I want to load my model in how many devices, or rather the GPUs, which are equivalent of GPUs, which are available. So I have the tensor parallel degree, and I can use that to configure how many devices am I going to use. Now note the key difference, that a tensor parallel degree of 4 is loading it onto 2 devices because each device comes with 2 cores. So a tensor parallel degree of 4 means I'm going to use 4 cores, and so it's going to use 2 devices when I specify this particular value. So that's the key difference between an Inferentia 2 instance versus a G5 or a P4D instances on SageMaker. Other than that, the stack remains the same. We have a large model inference container where we are going to load the model from the S3 into the container, and it's running on the Inferentia 2 EC2 instance. You can pick a variety of instances which you want to do. The one which I'm using is an 8x large instance for compiling the models, and then for hosting the model, I'm using an Inferentia just an X large instance to do this. And so let's look at some of the key areas of LMI containers, right? So again, we have made available the BF16 Neuron compile weights in public S3. So you will be able to pretty much leverage those weights and run your workloads. This notebook actually leverages that, so you don't have to do the compilations. But if you're interested, there'll be a notebook available which will show you how you can do the compilations for Inferentia 2. So here I'm just basically specifying, okay, here is where my model weights are. And to create the model.tar.gz, we are going to use a no-code option. So we are going to have only serving.properties. And if I look at serving.properties, and we'll talk about why some of these are important for the Inferentia. When I look at the serving.properties, if you remember from the earlier NLP demo we saw, some of them will start to look familiar to you, right? So the key is the engine we're defining is Python. And so what we're saying is we're going to use the DGL Python engine to host this specific model. Entry point, in this case, we're going to use a transformers neuron model, which is going to be handling your inference workload. And we'll take a look at this class as well. Similar to earlier, S3 URL goes into where and how my model weights are. Tensor parallel degree gives you the number of cores. Remember this, it's important here is number of cores versus the number of GPUs which you're going to use to define your model. And then of course is your D type. Here I'm saying BF16 because I'm wanting to run this on a BF16 workload. So this is all what you need to really define your endpoint in SageMaker. Just this properties file. The rest of the code is very similar. We create a model.tar.gz and upload this to SageMaker, and the rest of the code is I'm going to use the inference image, which is going to be the deep speed one, which has a stable diffusion built in. Create my model. Here I'm showing you Boto 3. If you remember the earlier demo, I was showing you the Python SDK. You can use either. I just wanted to give you both the flavors. So we're using Boto 3 to create the model, and then we create the endpoint config, and then essentially we do the hosting. And once the hosting is done, then I can pass in the text. In this case, I'm passing in mountain landscape as my text. And when I run this, I basically get a nice, beautiful image of a mountain landscape in a 512 by 512 instance. Now you can, of course, specify higher precision. If you want to do, say, 784, you'll have to compile the model for a 784 instance. Now, before we look at the inference, the Neuron Python file, which is handling the inference, let's take a look at some of the key concepts. So in a stable diffusion, it's really a sequence of three models. That's really what stable diffusion is. So your key model is the unit model, which is handling most of your denoising and noising steps as you're going through the inference workload, right? So when you're compiling your weights, you will need to make sure you compile for the Neuron SDK, the unit, the V8 decoders, post-quant, and also the clip text. So I made a mistake where one time I did not do the clip text and I saw my inference time just jump up. So it is a combination of all four. You have a text coming in, so you need to have that also in a highly optimized way because you're going to create the embeddings, which is going to match, which is going to be used effectively to do the image generation using the denoising steps. And then, of course, you have your unit model, which does all the beautiful work behind the scenes, and then you have the VAE. The second point to note is for the cross attention scores, there is an optimized method which has been used in the Neuron LMI container SDK, which brings the inferencing time significantly. So doing all of this, I'm able to now run a 512 or 512 image in about 1.9 seconds or using Inference Chat 2. And if I skip and let's take a look at the Inferentia 2 file, and then we will effectively wrap it up. So here is the handler, which is the default handler for Inferentia 2. How is the default handler set up? And if you see over here, there are some certain unit specific classes which we are creating. And then, of course, we are also creating the text encoder classes. And then here is the attention score method, which I mentioned is optimized, which needs to be replaced. Other than that, the entry point, let's start with the entry point. The entry point is the same place. We basically have what we call as infer. And in the infer, I'm basically getting all of these properties where I'm going to get my parameters, the prompt, which I'm trying to do, and then I just call my self.pipeline to run through the image, get the image, and then effectively create a buffer out of it, bytes buffer, and then add it to the output and send it back to the calling user. And for loading the compiled model, we are going to be loading those four key compilations which we did. So we're going to load the text encoder, quant, UNet, and the VAE decoders. Now, the LMI container does let you also do runtime compilations in case you are just wanting to run some sort of quick test. You have the option of specifying a runtime quantization, runtime compilation as well, in which case it'll take the raw weights which you specify, compile them, and then load them onto the GPU and make it available for serving. So that option remains, but the usual recommendation always is to do ahead of time compilation. That's where the save compile method is coming in. Feel free to look around this class. You can adapt this class to your specific workload. It goes into various compiler options and arguments. There's documentation available around this on the Neuron SDK websites, and we can work from there. And with that, we would pretty much wrap up our session of being able to host. So using this class, which is the inbuilt class, I'm going to just quickly run through the image one more time, where if I run a mountains landscape, or this time let me run a slightly different one. I'm going to basically run, for example, houses on snow-capped peaks, right? So I'm going to run this example. And then, of course, once the results come back, let's see how the image looks like for snow-capped peaks. So voila, there you go. I'll zoom this out so we can see the image slightly better. It basically, showed me beautiful houses flanked by snow-capped peaks. So that's all for the LMI container. In today's session, we've shown you how you can use LMI containers to host NLP, generative AI models, how you can host Stable Diffusion, generative AI models using the LMI containers. We've also shown you the Neuron compilers and how you can use Inference 2 to run some of your workloads. And we will have the links out there. Happy learning. And that should conclude our session for today. Thank you.